Hello. Today we will examine some different reference frame to study the geometry of space-time around gravitating bodies. In particular, we will start to study black holes. Before to do it, I want to remind an important feature. We have seen that the for a central mass m, we can write the Schwarzschild metric. That is this one. Okay. Where this is the radial metric, just considering a spherical symmetry, and we know that the gravitational radius, or Schwarzschild radius, Rg, is equal to 2g over c squared. Okay, so depends just only by from the central mass of the attracting body. So we have seen also that, for instance, for the Sun, the gravitational radius is about 3 kilometers. Okay, so this is an interesting case, because when the radius, like in this case, is just smaller than the this is 3 kilometers, and this is not in scale. I mean, this is 100,000 kilometers, or what is it? The radius of the Sun. This is, in this case, is incredibly smaller than the real radius of the Sun. So this formula doesn't work in a proper way, because the mass m is not contained inside these 3 kilometers gravitational radius, but is distributed also outside. So this is this value here doesn't represent anything physical, no, because the mass that determines this value here is distributed also outside. Different is the case in which we have an opposite situation. Suppose that we could concentrate all the mass of the Sun inside a sphere of radius 1 kilometer, so less than this. You have a situation like this. In this case, this is the Rg. Better if I do in a dotted way. Okay. And the mass of the Sun is contained in, so this is 3 Rg is equal to 3 kilometers, and suppose that the radius of the mass of the Sun in this case is 1 kilometer. Okay, so this is another situation. In this case, all the mass m is inside this sphere, and what happens? That this is what we call event horizon. In this case here, we have that nothing can get away from this distance here from the center of the mass, and this is, in this case, we have created a proper black hole. Okay? Black hole, right, just because nothing can come out of this limit, and neither light, and this is the real meaning of black hole. Obviously, in a case like this, we cannot have a structure of 1 kilometer, a sphere of 1 kilometer inside the event horizon, because this mass here cannot stay still at distance 1 kilometer from the center, and everything, all this stuff here, continue to collapse towards the central singularity. This is the result that we have in a situation like this. All the stuff outside that falls inside continue to fall until the central singularity. We don't know the physics of the central singularity because we have not a quantum gravity theory at the moment, but we can guess that at least until the distance between from the singularity is of the order of the Planck length, the stuff continue to go there. Okay, this is the representation of the black hole, and we will study it in great detail, and then we will use this equation again and again, but we have to remember that this is properly valid, written in this way, until we reach the distance from the center equal to rg. This equation here shows that if r is equal to rg, this is 0, this is 0, so we lose significance of the equation, and we must use other, we must perform some coordinates change just to afford this particular situation. So this is very good to describe all the space-time outside the horizon, okay, and we point at a certain radial distance from the center, but it fails to describe the situation inside the horizon. Okay, let's start to consider different frames to study black holes. Okay. We have already seen in details two of them. The first one is the so-called faraway observer frame. Far away observer. We know what is it. It is exactly this situation. Suppose that this is the central mass, the black hole, and this is the RG sphere, the event horizon. And let's go in a radial direction. And very, very far away we have our observer, and this is the FA, the far away observer, and this is infinite, the distance infinite. Okay. We know that for him, or for R, the description of the geometry of the space-time is given by the Schwarzschild metric, that is the one that I've written just before. We have seen also the free fall of observer. Okay, in particular, we have considered, for simplicity, an observer falling down towards the center of the black hole, just along a radial direction. So we don't study for now a situation like this, where this situation should bring to an orbit like that, a deviation. But we want to study the simple case of a radial motion. So not transverse direction respect to the center of the black hole. Okay, and in this case we had a body, suppose here, falling down with a certain velocity, okay, and the idea is just for simplicity to consider a freely falling observer, okay, on board of this object. The freely falling observer that starts falling down from an infinite distance where the faraway observer is, okay, with an initial zero velocity, with an initial zero speed. What means? So it means that suppose that this man here is just on board on a spaceship here, at rest, and suddenly, but slowly, it starts to feel the gravity from the black hole, and so the initial velocity is zero and starts to fall down like that. It's just the same example as you drop a rock from the top of a cliff, okay, with initial zero velocity. You could decide to push it, so to let it start with an initial velocity, but this is simpler for many practical reasons to leave it fall down with initial zero velocity. The substance doesn't change at all, just the formulas are more simple, but we can change them introducing initial velocity if we want. But for the moment, let's consider this frame of reference of the freely falling observer, and we call it a rain frame observer. Rain frame, so RF. Why? Because the rain falling on the earth exactly start falling with initial zero velocity. When the little drop of water starts falling down, it starts with zero initial speed, and the velocity increases falling down. It's exactly the same. Okay, this is the second observer that we have already studied. Okay, there is a third interesting possibility, is just to imagine that we have a shell, a spherical shell at a certain distance from the center, let's call it R0, constant, okay, and we can imagine that you can imagine this like an artificial structure made of very, very strong bars together, sustaining an observer standing still here, okay. For instance, for example, the surface of the Earth, the ground, is just a shell, because it is not a black hole, the Earth, obviously, but there is it is a massive body, and we feel the attraction of the Earth standing still on the ground, and this is the effect of the distortion of space-time, and we live on a shell, and our shell is just the surface of the Earth. You can imagine something like that. You have a mass here at the center, and you have a ground, an artificial ground built around this black hole. Another way to do it is to to have here, for instance, a rocket firing with the engines on and pushing the fuel away, and so this push here maintain it at a constant distance r0 from the center. In this way, a person inside the rocket feels a strong gravity because it is standing still, and all the gravity is acting on the poor body of the astronaut. Okay, the same of this person standing here on the shell. We feel on the Earth a pleasant gravity, but you can imagine if instead of the Earth we had a black hole, a very massive black hole, and underneath, we should die quite immediately because of the strong tidal forces. But anyway, this is the third reference frame, the shell observer. Okay, and we call it S shell. Okay, SH shell. Okay, before going on with calculation, we have to do some considerations. First of all, let's look at these two frames. Okay, the faraway observer and the rain frame observer. What do they have in common? You can see easily that from a physical point of view, they both are inertial frames. The reason is quite simple, just in an intuitive way. The faraway observer is imagine like an astronaut floating in the empty space, very far from the black hole. He is floating just without any gravity in the empty space. So the space-time is flat for him. You can see it easily because for him the Schwarzschild metric has the simple form is delta S square is equal C square delta T square divided 1 minus, multiply, is C square times 1 minus G over R, but R is very big, is infinite. Let me write this, is not very rigorous mathematically, but just to understand, so that this term here is 0 because it's Rg divided a huge number times delta t square minus the same delta square divided 1 minus something very little, Rg over infinity. So these two factors are 1, and so T and R are exactly the proper time and proper space when the far away observer observes things, phenomena just around him in this very far away space from the black hole. This is flat space-time, okay? Well, the same is not the same, but a similar situation is for the rain frame observer, because we know that for him he doesn't feel locally the gravity, because he is inside the spaceship falling down radially towards the black hole. And for the Einstein equivalence principle, is just in free fall, and it doesn't feel any gravity. It's just floating in the same way this band is floating in the empty space. So this is another inertial frame like this. And so you can perform from this reference frame to this reference frame just the Lorentz transformation of the special relativity. You don't need to use general relativity calculation. You don't need to use the Schwarzschild metric when you compare space-time of these two guys. Okay, this is very important. The situation is radically different for this person here, standing still on the shell, because for him the situation is just like for us on the Earth. The ground of the Earth is just our shell. We feel gravity, and he feels a strong gravity, and he measures a proper time and a proper space here around him if he wants. So let's go to compare some space-time interval between two events as measured by the shell observer and the faraway observer. Okay. Oh, for him, simply, you have that. Suppose that he has a little ball, and he lets the ball go horizontally on this surface, so that there is no change in the radial direction. For the distance, the space-time distance of these two events, start and arrive of the ball, is just delta S square is equal to what? To C square delta tau shell square minus delta R square shell. Okay, because locally it doesn't need to use the Schwarzschild metric. This is the proper time and this is the proper space as measured exactly here. You need the Schwarzschild metric for this guy here when you measure the same in space-time interval between the two events related to the ball. His measurement is just delta S square is equal C square delta T square, C square 1 minus Rg over R0, that is the distance of the shell from the center, times delta T square minus delta R square over 1 minus Rg over R0. Okay? But listen to me. We have said that the distance, the space distance is just from these two events is just tangential. It is not radial, so there is no variation along the radial direction. So for both of them, this term and this term, because delta R shell and delta R far away, they are, as measured by the far away, they are all zero, or both of them zero. And so, finally, we can equate these two terms, because we know that the space-time interval as measured by this man here is exactly the same as measured by this one, and so the result is that when I do this equation, I can cancel the c square and I can perform immediately the square root, and I have that delta tau shell is equal to square root of 1 minus Lg over R0 delta t. This is a very important result. We can interpret it immediately, and you see that if R0, that is the shell distance, is very near to Rg, this number is very near to 1, so this, the square root of this is just a small number, so the time interval as measured on the shell is much smaller than the time interval as measured by the faraway observer. You have seen this result in the, for instance, in the movie Interstellar, where some people are staying on a planet orbiting very near to a black hole, and so R0 is very near to Rg, and if I well remember, every 1 hour spent on the planet corresponds to, if I well remember, more or less 7 years just on the Earth far away. Okay, that is just a little bit more complex situation, because the planet orbiting is just not like standing still on a shell, but you should consider also the speed of the body around the black hole, and the calculation is a little bit more complicated, but it is not drastically different. So this is the first important result that we have when we compare the shell observer results with the faraway observer result. Then in the next talk we will compare some observation performed by all the three different observers, and we'll find some interesting issues. Thank you very much.